My students have just come into class and right now they're working on their Do Now assignment. On the board I have posted a question, and this is a question related to what we've covered, either what we've covered the last time from the last class or something that's related to what we're going to be doing today. So right now we're actually doing something related to what we're going to be talking about. So we're going to be scaffolding knowledge. Students are assessed right at the beginning of class through this Do Now assignment because they're actually texting in their answers. In a few minutes we'll get some poll results from what my students have entered while they've been working on their problem. So we're going to reveal our poll results here. And it looks like 92% of our students answered A, which was the correct answer for this problem. So now we're going to go ahead and look. We had one person chime in with a different answer, and I can understand how you might come up with that because what happens in this problem is, or in this answer, is that the slope here is positive when it really should be negative. Today, class, we're going to be talking about what it means for a function to be one-to-one, and we're going to find out what it means for a function to have an inverse. So what we're going to look at is a simple process, and that is the process by which our computers use binary code to go from a 1 or a 0 to maybe a character that's output on your screen. So let's think about this. When we use our computers, we type up our paper for our English class. We're typing away. Well, every time we hit a keystroke, it transmits a signal to the computer, and it takes that letter, suppose N, and transfers it into a 1 or a string of 1 and zeros. And then from those 1s and zeros, it transfers it back to the screen as the letter that we see that forms the letter N. So we went in one direction, and then we came back. So we had one image and a pre-image, and we're going to talk about that in a minute. But can I have a volunteer that can help me with this binary code, because I have some binary code here on the screen and I have no clue what it says. So can I have a volunteer? Okay, why don't you come on down, Nick, and help us out. So Nick, all you have to do is click this computer, and then you're going to go ahead and click it. One more time. There you go. All right, now Nick, what you're going to do is hold on right here, and then you're going to paste the code. There you go. All right, Nick, now can you translate that for us? Click the button that says to text. So what Nick is doing is he's transferring binary code into text. So Nick, what is the text that binary code said?
I love Mr. Colunga's pre-cal class.
Well, thank you very much. I appreciate that. We're going to talk about what it means first for a function to be one-to-one. So let's think about this. For a function to be one-to-one, the definition of a one-to-one function is this. A function with a domain A is called a one-to-one function if no two elements of A have the same image. That is to say that for every item in A, you have an item in B, a unique item. Okay? So let's look at these two functions, f and g. Every item in A must map to only one unique item in B. So here we go from 4 to 10, 3 to 7, 2 to 4, and 1 to 2. This function is said to be one-to-one because it maps to a unique value from A to B. But what about this function g? Is this function one-to-one? Let's stop and think about that for a second. So take a look at it. Okay? The question is, does it map to a unique value for every item in A to a unique item in B? No, it does not. So the next thing that we're going to be talking about are the inverses of a function. So let's take a look at this definition. It says, let f be a one-to-one function with domain A and range B. Then its inverse function, f inverse, has domain B and range A and is defined by the following function. F inverse of y equals x if and only if f of x equals y. for any y in B. Okay? So it sounds kind of complicated, but when we think about it, I can use a very simple example to help explain this. So, who remembers cameras that we might have used maybe 10, 15 years ago? Okay? A camera that had what inside of it? Film, instead of a memory card, right? So the film, you'd take your pictures. What would you do with the film then? Okay? You'd take it to the grocery store or, Walmart, things like that. Get the film developed. Then maybe a few days later, you'd get your pictures back. What came with the pictures? The negatives came back. Very interesting name, negatives. Think about this. The image is our picture. The negatives are what we call the pre-image, right? It was the picture that had yet to be developed. So it's kind of interesting that an inverse uses f to the minus 1. Yes? Because notice we are going from here, the pre-image, to the image. Okay? This is perhaps those negatives. And then this is the photo that gets developed, right? And the inverse is simply going backwards. So suppose you went from the picture back to the negatives. Notice F inverse right here. So for this next part of the activity, I'm going to be handing out some mirrors, and we're going to take close attention and look at number 10, and I'll explain what we're going to do with the mirrors in a minute. So let's just pass these out. Now what you're going to do with the mirror is on problem number 10, I want you to take your mirror and hold it on this dotted line right here, right about where they intersect. Okay? Hold it right about there. Now what you should start noticing, if you look through the mirror, is that you should see the reflection of that graph on the other side. Yes? So what we're determining here is whether or not these two functions that are graphed are inverses of each other. Okay? So take a look, and we're going to check if they are. So on number 10, what do we see? Do we see the reflection? Yes. Okay? So we see the reflection there. Now let's go ahead and take a look at the very next one. All right? So hold your mirror up against your graph and tell me what you see on number 11. You see the reflection on the other side. Well, what this mirror is, it's not a mirror anymore. This is the line y equals x. So the graph of f inverse is obtained by reflecting the graph of f, which was the original graph, across the line y equals x. And that's what this dashed line represents, the line y equals x. Now what we're going to do is we're going to go online and we're going to take a quick quiz on infused learning. What my students are doing right now is they're taking a quiz on their iPods or iPhones or smartphones, and they're on what's called infused learning. And the cool thing about infused learning is that I get up to the minute results for their progress. So they're in the process of taking a quiz, and as you can see, some of them are completed. Every green mark denotes a correct answer, and every red mark denotes an incorrect answer. So I know while they're taking the quiz who understood a concept and who didn't, and then I can go in and focus on that student. And it really helps for a more one-to-one relationship with the student, because if I can assist every student every day, then my students gain so much more from it. At the end of the school year, I don't want the students to have remembered that I taught algebra or pre-calculus. I want the students to have gained math appreciation. And that's the ultimate goal, is that the students are able to apply what they've learned in the classroom, outside, in the real world. My name is Homer Colunga. I am an intern with ACT-RGV. I teach secondary math at Wesco East High School, and I am empowering 21st century learners.